let us start lecture 6, and the course is phase diagrams in single component and binary systems. Today we will try to look at equilibrium, internal energy, isolated system, enthalpy. These are the aspects we will try to understand. In fact, as we have been continuing on the concept of equilibrium, so we looked at the statement of first law also using internal energy, work and heat, and that first law talks about conservation of energy. So, we will start today from that. So, the first law of thermodynamics it is nothing but conservation of energy, and the statement says del U equal to Q minus W. And here a system is at A state and then it goes to B state, and there will be some heat absorption when the system changes from A state to B state, which is Q, and while having that change, system does some work W, and that gives you this statement of first law. So, you can see that whatever energy consideration we have, Q, W and U, they have a kind of equation which narrates the conservation of energy. Now, we will try to look at this equation more carefully, and we have already stated that internal energy is basically internal the energy within the system, and that comes from all the potential and kinetic energies of different particles that that particular system contains. Once we look at this particular equation, then you will see that what does that particular internal energy mean. And also we have stated isolated system, open system and closed system. We are pretty clear that open system is which actually allows mass and heat flow, heat exchange with the surrounding. Closed system, it can exchange heat depending on what type of wall it has. If it is a diabatic, then it cannot exchange heat with the surrounding, but if it is diathermal, it can exchange heat with the surrounding. But we have also talked about one particular system which is isolated. Closed system cannot exchange heat, cannot exchange mass with the surrounding, but isolated system cannot do anything. Okay. So, it is isolated from rest of the surrounding. So, we will also understand isolated, the concept, very concept of isolated system from this particular equation we can get it. Okay. Let us look at this equation. Now, if I talk about Q and W and if I write it in terms of differential form, it becomes like this. Why? Because U is also a state function, we can prove that. Okay. But Q and W, these are path functions. Okay. So, that is what this differential form is written like this. Now, we take an assumption. The assumption is whatever work component we have, those work component only contains mechanical work. Other work forms like magnetic, gravitational, all those work forms we do not consider for understanding some of the basic concepts of this particular energy equations. So, we have only mechanical work, this is mechanical work, and when we talk about mechanical work and if we consider gas expansion or contraction, then there will be a mechanical work content would be PV term. P is the pressure, V is the volume. Okay. So, that term we will consider only, and Q we consider in terms of heat, or we can say thermal energy. Fine. Now, that is one assumption we take it. So, if I consider some of the consideration, let us take it. One is, if we take this system to be isolated. Isolated means it cannot exchange heat with the surrounding. So, that case Q becomes 0, or I can say del Q becomes 0. So, now my equation turns out to be du equal to minus del W. And here whenever we have this minus sign, as we have considered in our last lecture, that when W, when the system does work, that W will be positive, and when system absorbs heat from the surrounding, that Q would be positive. So, here in that concept of this particular equation was built up. In fact, if we look at other end, if we release heat to the surrounding and the system releases it, and that time the work will be done on the system, still you will get this equation. Okay. So, now here I am considering work that is done by the system. Okay. That is a consideration we take it. Even we can also get it if the work is done on the system, still similar type of equation will evolve. Now, once we have this, then you can see that system cannot exchange heat with the surrounding, but still it does work. Now, we have considered that energy cannot be created or energy cannot be destroyed. Only possibility is energy can transform to another form. For example, when you have taken heat and work, at that time we have taken a kind of equivalence of work. So, that time we took it as Q equal J W equal to J W, and J becomes my equivalence. So, equivalent amount of work, equivalent amount of energy will be evolved. Okay. So, if you see previous, if I go back to previous equations, let me just show you, we talked about this, you see this equation. Okay. So, this J becomes mechanical equivalence of heat. Now, coming back to this, so that means du is basically change in internal energy and W is the work done by the system, and I have not added any heat from outside. So, and still the system does work. So, that means the system must be having some form of energy, okay, and that is nothing but the internal energy. So, that is what this is, my internal energy. Otherwise, system cannot do work. Okay. Now, this work is done. So, this gives you a very concept of isolated system. Isolated system can do work provided it expands, provided that internal energy is spent or internal energy converts to work. Now, if I consider this very equation, now we got to know that what does that isolated means and how come it is related to internal energy, and the system must possess some energy within. Now, let us take this one further. Now, U can be related to a function of V and T. Okay. Now, once we have this, then I can write it like this. This partial form we can write. Now, here if I take this as a constant volume process, if it is a constant volume process, so that means this term goes to 0. So, it ends up dt. And we have seen that du equal to del q minus del w. Since we have taken only mechanical work, this goes to 0 for constant volume process. So, du equal to del q, and since it is a constant volume, I can write a small superscript b which indicates constant volume process. So, I can replace du equal to del q v dt, okay, dt, which is constant volume. So, here since I have taken this v inside, so I can write this. Now, what does it mean? It means that per unit change in temperature leads to a certain change in heat. Okay. So, that is nothing but heat capacity. Heat capacity, this is termed as C, and since it is at constant volume, so I will write Cv. This is heat capacity under constant volume condition. So, this equation will be Cv dt. So, now final equation becomes du equal to Cv dt. Now, here if the change in, for example, if internal energy of a system reduces, so that means definitely from this equation I can get to know that temperature goes down if U goes down. Okay. So, this is a kind of correlation we can find. So, here also I would see that system temperature would reduce for isolated system where there will be no heat exchange with the system with the surrounding. Now, once we have this, then I can now write the full equation Cv dt equal to del q minus del w, and which is coming from du equal to del q minus del w. So, this turns out to be this. Now, if isolated again, let us consider that if isolated, then del q equal to 0. So, it goes to Cv dt equal to minus del w. Now, once we reach there, let us take one concept into picture. So, let us take a situation. I take an ideal gas and this is contained in a frictionless, this is contained in a chamber, and that chamber has a piston which is frictionless. So, there will be no friction here. What does it mean? That if there is no friction, that means there will be no work done when this particular piston goes up and down. So, this is an ideal gas. Now, this piston exerts some pressure, the system exerts another pressure. Outside we have a temperature, inside we have a temperature. Now, if it is equilibrium, that means I would say that T1, T2 for system, let us take P1 and outside pressure P2. So, if P1 equal to P2 and T1 equal to T2, the system is in equilibrium, and since it's a single component ideal gas, so we don't have to bring in chemical equilibrium because everywhere the composition will be same. So, this is equilibrium. Now, let us say I reduce this pressure by a small amount, and this small amount is infinitesimal. So, this is infinitesimal change. So, that means extremely low change in pressure. So, that means pressure is reduced to some extent, and because of that there will be a small change in volume also. This particular thing will reach to this place, that piston will reach to this place. So, actually my change would be this much, a meet path. Let us say these changes dV, and this change is so infinitesimal, small that the system may not experience that change has happened. This is a very unique concept. So, if system does not see that change has happened, that means system remains under equilibrium, system feels that it is under rest, and we have what we have considered, that system will be in equilibrium if system feels that it is under rest, under the influence of nearly unchanged variables which are defining the system, okay, or system state. Initially we started with that definition, that system which is left to itself will not change its state provided the defining parameters for the system are not changing. Now, I am changing a little bit, that system would feel like it is under rest provided that there is a kind of very insignificant change in the very infinitesimal change, a very small change, as if there is no change. So, this is as if there is no change. This is a particular term which is used in thermodynamics, which is basically quasi change. Quasi change, or we can say quasi static. It means that the system is changing in such a fashion that system feels that it is at rest. So, if system feels that it is at a rest, so that means the system state is also feeling that it is not changing. There is actually a infinitesimal change. So, system in this fashion, there is a small tiny amount of change happening, and then finally, if you see that there will be a kind of finite change, but system would not leave the equilibrium state. This is a concept which is used to define concept called reversible system. Okay. So, reversibility does not mean that it should not change, there will be change, but that change will not be felt by the system during those infinitesimal changes, step changes, infinitesimal step change. So, the system remains under equilibrium. Okay. So, that is the concept we are using. So, if that is the case, the system feels that it is under rest. So, then what will be the work component? Work component would be, del W equal to P minus dP del V. So, now if we expand it, P dV minus dP dV, since dP is infinitesimal, dV is infinitesimal, so that term becomes extremely small, we can ignore. So, if we ignore, then finally it comes out to be P dV. Now, here all those quasi-static changes that is taking place, so it actually remains, for example, state 1 to state 2, when it goes, the system goes under the influence of quasi-static change. So, then it actually experiencing a reversible change. So, the reversibility is nothing but the system does not leave the equilibrium surface. Now, let me just relate this equilibrium surface with the diagram what we have learned before. That time we couldn't understand that whether what happens when a system goes from 1 to 2, okay, state 1 to state 2, in between two paths we have considered, if you recall that we have considered two paths, one A2 and another one is 1 B2. I will show that picture, I will draw that picture, and you will see that in that particular plane the system actually remains under equilibrium and still the system changes its states. So, that particular plane is basically equilibrium plane or surface, you can say. Okay. So, that change can happen if there is a quasi-static change or a reversible change. So, now if I try to look at that particular diagram, so if I go back to that diagram, so it is basically plot between volume, temperature, and pressure. So, there we saw state 1, state 1 to state 2. So, it is one case it is going to A, this is A position, this is one position, and then it is changing to 2, and then another path is B position. So, it is changing to this and then coming back to this. So, these are the two changes, two paths, and we have decided those paths in such a fashion that 1 and this is 2. So, the 1 to A, it goes through 1 to 8 goes through a constant pressure process. So, this is my 1, this is my 2. Now, this is the projection on this PT plane. This is A, I can say A prime, 1 prime, 2 prime, prime are basically those projections, and then B goes here. So, the B point is such that it actually from 1 to B, it will be a constant temperature process. A to 2, it is a constant temperature process, and then 1 to A is a constant pressure process, and B to 2, it is a constant pressure process. So, this is the change that is taking place. When we have a projections, this is basically B prime. Okay. Now, that time, so this is P1, P2, this is T1, this is T2. This is T2. So, that time if you see that this plane is actually equilibrium plane if we have those changes in infinitesimal amount. So, that means 1 to A and A to 2, everything is happening under a quasi static change mode, okay, a quasi change mode or reversible mode. So, this will be my equilibrium surface. So, when we have this, then I can write del W to be P dV. So, then I take this equation which is Cv dt equal to minus del W equal to P dV minus. So, this is one equation we are getting. Okay. So, this equation talks about adiabatic change as well as, since we can write this only when it is a reversible process. Okay. So, then only this equation can be written. In fact, you just go back and read little bit of, you can go to the first law part, any textbook you take. So, there you can actually prove that P V gamma equal to constant. From that equation one can derive this equation, where gamma is a constant which is Cp by Cv, and Cp is basically the heat capacity under constant pressure, and Cv is the heat capacity under constant volume. In fact, there will be a relation Cp minus Cv equal to R, which is the universal gas constant. So, these two equations you can see there could be a possibility of small problems, you can solve those to understand better about this. So, this is one such situation, adiabatic change and reversible process. So, that means say isolated system, any change that is taking place would have gone through adiabatic process. Now, you can actually have reversible process, you can actually have irreversible process, and in case of irreversible process, please understand that it would not be on the equilibrium surface. It will be away from that equilibrium surface, and that is what it will be extremely difficult to understand the in between when the change is taking place, what state it is in. So, irreversible change happens without staying on the equilibrium surface. And in fact, when we come to the second law understanding, then you will see that all the natural processes are irreversible. They would not follow in between equilibrium. So, they goes suddenly, there will be a sudden change, or we call it spontaneous change. So, this is one. So, let us understand little bit about the Cp. So, in fact, when we talk about Cp, let us take it, this Cp we have to understand. Cp is heat capacity at constant pressure. So, that means since Cv we wrote like del q v dt, Cp can be written as del q p dt. Now, in order to get to Cp, we can bring in another function, which is basically, let us say I have internal energy U of a system and I take PV term. So, if I add these two and if I consider that the system only possesses mechanical work term, so then I can say that internal energy is the system within and PV is basically the external influence. Okay. So, that time we can say that this is my total energy of the system, because I have not considered any other energy form. So, that becomes my total energy of the system. Or we can say heat content of the system. So, this is termed as H, which is nothing but enthalpy. Okay. So, this equation I can write it like this, del H equal to, H is also a state function, del U plus P dV plus V dP. I can write this, and why are we writing like this? Because P is a state function, V is a state function, and U is also a state function. So, everything becomes a state function equation. So, now I can write that if P is constant, I can write it like del H equal to del U plus P dV. So, I can write this. So, this becomes P, because it is a constant pressure. So, now if I again put it like this, as a function of P and T, I can write del H equal to dou H dou T P dt plus like this. So, now since pressure is constant, so this becomes 0 and this is nothing but, this becomes this part become, I can write this del q p del t dt. So, dH equal to, we have defined already, Cp dt. Another equation we got. So, here we see that H, which is the enthalpy of the system, that is related to this del H equal to Cp dt. And in fact, if you see that if enthalpy goes down, that the temperature should go down, okay, like that way we can relate, just like del U equal to Cv dt. Now, if I come back to this equation, which is du equal to del q minus del W, if I consider isothermal situation, so isothermal situation means del T equal to 0, and let us assume that the system is able to exchange heat with the surrounding. So, that means even if the system does some work, then that work would be decided by the amount of heat the system absorbs from the surrounding, or any work is done on the system, then that negative work would allow some heat to expel from the system to the surrounding. So, this is the situation. Now, we know del U equal to C V dt. So, this goes to 0. So, U equal to 0, fine. So, if del U equal to 0, then I can write del Q equal to del W from here. Once we write that, then I can put it like this, equal to P dV, considering it is a reversible isothermal, change. Once we have this, then I can, if it is ideal gas, then I can put it, since we have considered ideal gas, RT, and if it is 1 mole, RT by V dV I can write. So, I can calculate the total heat as RT V dV V1 V2. This gives me the total heat that needs to be converted if it is absorbed by the system from surrounding to work. And you see, in case of reversible, since it is a reversible process, the entire heat that comes in from the surrounding, that goes to work. So, there is no loss of work. Okay. So, this loss of work and no loss of work. So, here at least in the reversible case, I could see that entire heat goes to work, but there will be situation when it is irreversible, and in case of irreversible, we will see that there will be some loss of work, and this loss of work would be an interesting consideration, and that would actually allow us to understand one particular term called entropy, and that entropy consideration will be taken in the next class. Let me stop here. Thank you very much.